Guys, are you able to hear me?
Yes, sir.
Okay. So I think we'll be completing this chapter today. So till now, did you face any difficulty in this chapter? The only difficult part that is there in this chapter is elementary operations, that is removed. Okay. That is the only useful part that is removed. Okay. So I'm expecting you guys to solve the exercise. Okay. So you have any doubt, you can reach out to me. Now we'll discuss the last part of this chapter, which is called as transpose of a matrix. Okay. So as the name suggests, transpose here means, any idea what is a transpose? Let's see if you guys can guess. I am hiding this. What is transpose? Any guess? Shifting the rows and columns. Shifting the rows to column. That's right. So it's basically interchanging the rows and columns. That's it. Okay. So if I have a matrix which is 3, 5, root 3, 1, and 0 minus 1 by 5, which is of the order 3 cross 2. Okay. Now, if I write the transpose of it, I'll write a power t, or I read it as a transpose, or you can also write it as a prime or a dash. So these are all the notations that are used. A transpose or a dash, which is again going to be the transpose. It becomes something like this. The elements in the column will become the elements in the row. And elements in the second column will become the elements in the second row, which is of the order 2 by 3. Are you guys able to understand? Right? So what I'm trying to say is, if A is a matrix whose elements are given by Aij is of the order m cross n, then the matrix that is obtained by interchanging the rows and columns of A is called transpose of A. See, the transpose is very, very important because there are many applications of it. One is something to do with matrices called as skew matrix, symmetric matrix, and skew symmetric matrix. And secondly, it has something to do with the inverse of a matrix also, which I'll explain it. Okay. So please give me a confirmation if it is clear till this step.
Yes, sir.
Clear, no? Okay. So based on the definition, there are certain properties that this transpose of a matrix exhibits. One is, if I find A transpose, okay, and the transpose of A transpose, okay, then I'll get back the same matrix A. Okay, see, if I have two matrices A and B of suitable orders. So one point that you can notice stands for you to find the transpose of a matrix, it is not necessary that it needs to be a square matrix. It can be a rectangular matrix also of different number of rows and columns. Suppose I take a single matrix and I find the transpose of it. To the transpose of the matrix, if I find the transpose again, I'll get back the original matrix. That is the first property. Second property is, if I multiply a matrix with K and I take the transpose of it, it is the same as multiplying K with the transpose of the matrix, in the sense, you first itself multiply the matrix with that scalar and find the transpose, or you first find the transpose and multiply it with the scalar. Both will give you the same result. Okay, I'll just be back in a minute. Okay. Next is, if I take the sum of two matrices and I find the transpose of it, that is the same as finding the transpose of A independently and adding it to the transpose of B independently. Okay. And the most important point that you need to observe here is, if I have the product of two matrices and I find the transpose of it, that will be exactly equal to B transpose into A transpose. Any guess why it is happening? Let me see how many of you are able to think out of the box. Why are things getting swapped? Just a minute. Somebody is calling. Just a minute. Sorry, guys, an urgent call. Had to take it. Suprajit has messaged. Because in AB, the rows of A and multiplied with the columns of correct. And in B dash A dash, the columns of B will be correct. So what will happen is, when you find the transpose, right, the order of the matrix will also change, right? And what is the necessary condition for multiplication? The number of columns in the first matrix should be exactly equal to the number of rows in the second matrix. That is why if you take AB and multiply, if you multiply AB and take the transpose of it, it need not be exactly equal to A transpose into B transpose, because the order will change, so that the matrices A transpose and B transpose might become not fit for multiplication if you take it in the order of A transpose into B transpose. Is it clear? So having said this, can we try out few problems? See, if you see, by now you should have understood one thing. Whatever properties you are learning, right, problems are based on those properties only. For example, here you see A is a matrix and B is a matrix of suitable order. They're asking us to actually verify the corresponding properties. If A and B are square matrix, then yes, but that is one of situation. We didn't mention a condition saying that for you to define the transpose, it has to be a square matrix. If you say that, then AB transpose should have been A transpose into B transpose. No, still it will not work. Still it will not work because the rows and columns will get interchanged. If you see the multiplication process, so I want everybody to read the comment of what Suprajit has asked. Sir, if A and B are square matrix, then is AB transpose is equal to A transpose into B transpose? No, because what will happen is since the columns and the rows will get interchanged, what is the basic process we follow for multiplication? The numbers in the rows of the first matrix will get multiplied with the numbers in the corresponding columns of the first matrix, of the second matrix, right? But when you swap it, right, here columns will become rows and the rows here will become columns. So you still have to follow the process of B dash into A dash. Think about it, you will get the answer. Yes. So can you guys do this problem? A transpose, the whole transpose. So what is A transpose, guys? 3 root 3 2 4 2 0, correct? So what is A transpose transpose? That is 3 root 3 2 4 2 0, correct? Similarly, if I take A plus B transpose, so what is A plus B? 5 root 3 minus 1 4. Sorry, first let's find A plus B. So 5 4 and 4. So then what is A plus B transpose? Is there anyone facing difficulty in solving? Okay, 5 5 root 3 minus 1 4 4. Is it right? Now, what is A transpose plus B transpose? You want, you can do and see, you will get the same answer. Fine. Is it clear? Similarly, if you want to find K into B, if you want to find the transpose of K into B, what will you get? K into B is 2K minus K 2K, K 2K 4K. If you find the transpose of it, how much will you get? Hmm. 2K minus K 2K, K 2K 4K. So if you're going to find the transpose again, so 2 minus 1 2, 1 2 4, and multiply this with K, you're still going to get 2K minus K 2K, K 2K 4K. Is everyone clear? Give me a confirmation.
Sir.
Clear, right? Okay. So now you guys can try these problems. So I'll just give you one tip. The only thing you need to be sure of is concentrate when you're solving these kind of problems, because you're dealing with numbers. Sometimes even if one number goes wrong, right, the whole process will go wrong. That is the only concern with respect to this chapter. Otherwise, the theory part is very easy, right? Are you accepting, or you are saying the theory is tough for this chapter? Is it easy or tough?
Very easy, sir, compared to other lessons.
Yes. So because it's only about numbers and manipulations, that's it. You're going to multiply, subtract, add, or whatever you do. Okay. If you have two matrices where the first one is a column matrix of order 3 cross 1, and this is of the order 1 cross 3, then what will the order of the matrix AB be? So order of the matrix AB will be 3 cross 3, correct? So I'm assuming that everybody knows multiplication. So when you do A into B, you get -2, -6 and 12, 4, 12 and -24, 5, 15 and -30. Okay. Now, what we will do is, if I take AB and take the transpose of it, AB transpose, then how much will we get? -2, -6, 12, 4. Okay. -2, -6, 12,
4,
2, 4,
12,
5.
-24.
So the diagonal elements will remain the same, -24. Here it will become 15. Okay, this is what is AB transpose. Now you know what is B transpose, right? Can you find B transpose individually? B transpose will become 1, 3, -6, means a row matrix has got converted to column matrix, and A transpose will be -2, 4, 5, means a column matrix will get converted to row matrix, -2, 4, 5. Okay. Now, when you multiply these two, right, you should actually get AB transpose. If that part, I'm leaving it to you. You guys can try. If there is any doubt, reach it. Okay. So this is about the transpose of a matrix and their properties. Now, the next important point that we need to discuss is symmetric and skew symmetric matrices. So symmetric and skew symmetric matrices. Here, if you see, the definition starts with the word square matrix, underline that. So if you have a square matrix, then you can call that square matrix A to be symmetric if the transpose of that matrix is equal to A. Means if the when you do the transpose of that matrix and you get back the original matrix, then you call that kind of a matrix as symmetric matrix. So A is equal to √3, 2, 3, 2 minus 1.5 minus 1, 3 minus 1, 1. So what is going to be the A transpose of it? √3, 2, 3, here 2, 3. See, I'll tell you for a 3 cross 3 matrix, right? I'll tell you the way you can write the transpose. Listen, write down the diagonal elements undisturbed. Okay. Bring this one. So this 2, 3, bring it this side. So 2, 3. This 2, 3, take it this side. That becomes 2, 3. Swap this -1 and -1. So -1, -1. So unfortunately, the numbers here are the same. So you would have not understood what I wrote. Is it clear? So first write down the diagonal elements. Then at the first row and first column, interchange them. Then interchange this one and this one. You will get the answer. Right? So that is a symmetric matrix. Similarly, on a counterpart, you have something called as a skew symmetric matrix. What is a skew symmetric matrix? That is also a square matrix. A. You can say a given matrix is skew symmetric if the transpose of that matrix is negative of A. Okay. If the transpose of a matrix gives you negative of A, then you call that kind of a matrix as skew symmetric matrix. Okay. So there is one important property with respect to skew symmetric matrix. For a skew symmetric matrix, what should happen is the diagonal elements are there, right? They are always 0. Okay. For a skew symmetric matrix, the diagonal elements are always 0. Now, based on the basic definitions, what can happen is there is a theorem which says if I have a square matrix of order, a square matrix A with real number entries, then if I do the sum of A and A transpose, I will always get a symmetric matrix. And if I do the difference of A minus A transpose, I'll get a skew symmetric matrix. Is it clear? Is that clear? So if we have a square matrix A, where the numbers in that matrix, the entries of the entry that you have made is a real number, then if you add that matrix to the transpose of that matrix, then that whole matrix A plus A transpose is always symmetric. If you take the matrix and subtract the transpose from it, that is, if you do A minus A transpose, it is always skew symmetric. Okay. The next theorem that we are going to discuss is, if you take any square matrix, then you can always express that square matrix as the sum of symmetric and skew symmetric matrix. So how you can do that is, if I have the matrix A, then can I write this matrix as half into 2A? Correct? So can I write this half into A plus A? Then can I write this as half into A plus A transpose plus A minus A transpose, means I'm adding a transpose and subtracting a transpose, so that this A plus A transpose is always symmetric according to theorem number 1. A minus A transpose is always skew symmetric according to the same theorem number 1. So from this I can write A is equal to half into A plus A dash plus half into A minus A dash. Is that clear, guys? Is it clear? So these are all the properties that we need to understand. So based on that, there is an example. Suppose I have a matrix B, which is 2 minus 2 minus 4 minus 1 3 4 and 1 minus 2 and minus 3. Express this as a sum of symmetric and skew symmetric matrix. So how can I do that? So if you observe this, B is equal to 2 minus 2 minus 4 minus 1 3 4 1 minus 2 minus 3. Then what is B transpose? Now maybe see, write the diagonal elements as they are. So put minus 2 here. So interchange between these two, minus 2 and minus 1. Interchange between these two numbers, minus 4 and 1. Now interchange between these two numbers, minus 2 and 4. So when you do this, can I write B is equal to half into B plus B transpose plus half into B minus B transpose? So half is going to be there. What is B plus B transpose? B plus B transpose will be 4 minus 3 minus 3 minus 3 6 2 minus 3 2 and minus 3, sorry, 2 and -6 plus half into B minus B transpose. So what am I going to get there? B minus B transpose 0, -2 plus 1 is -1, -4 minus 1 is -5. -1 plus 2 is 1, 3 minus 3 is 0, 4 plus 2 is 6. 1 minus of -4 is 5, -2 minus 4 is -6, -3 plus 3 is 0. So you have expressed them. So they multiplied this half inside, this half also inside. So that is what they have written here. See. Is it clear, guys? Yes or no? Give me a confirmation.
Yes, sir.
So can I assume that you will be able to solve these problems? Yes or no? You can solve them?
Yes, sir.
So elementary operations are not there. I'll just explain one last concept of this chapter, which is called invertible matrices. Okay, that is, how do you find the inverse of a matrix? This one, how to find the inverse, we will see it in the next chapter after the concept called as adjoint of a matrix. Okay, so here we are going to discuss about what are invertible matrices. If A is a square matrix, okay, remember one thing, you can find the inverse of a matrix only if that matrix is a square matrix. If A is a square matrix of order M, and if there exists another square matrix B such that, okay, so other square matrix B should also be of the same order, such that if you do the product of A and B and you get a matrix called as identity matrix, then what we can say is, you can say B is the inverse of A. What inverse? It is multiplicative inverse. Is it clear? Because had they been numbers, what would have happened? When you multiply two numbers, you would have got the output as 1. Whereas here you're not multiplying the numbers, you're multiplying the matrices. So AB will be equal to I. Okay. Are you able to understand what I'm saying? Right? So here one important point that you need to notice, a rectangular matrix does not possess inverse matrix. Since for product B and AB to be defined and to be equal, it is necessary that the matrices A and B should be a square matrix of the same order. Because of the properties which are followed in multiplication, we can conclude the fact that rectangular matrices will never have inverse. And the second important point is, if B is the inverse of A, then A is also the inverse of B. Means if I write A is equal to B inverse, I can write B is equal to A inverse. That is what they meant. And the last concept of this chapter is, we have to prove that inverse of a matrix, inverse of a given matrix is unique. That is called uniqueness of inverse. Okay. So if you take the inverse of a square matrix and if it exists. So why they are using the word if it exists is because we have something to do with determinant. I'll tell you about that in the next chapter. So you have a square matrix, and let's say the inverse of the square matrix exists, then that existence will be unique. So how to prove that is, if I take A to be a square matrix of order M, and if possible, what we will do is, we will say A has two inverses, means we are trying to prove it using contradiction. Let's say A has two inverses, B and C. Okay, then we will show that B is equal to C. Then we can say B and C are same as it has a unique inverse, right? Now, if I say B is the inverse of A, then according to the inverse definition, I can write A into B is equal to B into A is equal to I. And let me call this as equation number 1. In a similar context, I can write, if C is an inverse of A, then I can write AC is equal to CA is also equal to I. Okay. Is it clear? Now what I'm going to do is, if I have the matrix B, then any matrix can be written as the matrix multiplied with identity matrix, provided it is a square matrix. Okay. So this I can write it as B into, can I write I is equal to AC? Correct? So we know the associative property of multiplication. So I can say this will be BA into C. But what is BA? BA is also I. So I into C will be equal to C. So from here I'm concluding that B and C are the same, which gives us a conclusion that every square matrix, if at all it has an inverse existing for it, then the inverse is always a unique inverse. Is that clear? Is that clear? Okay. The last one, it's better we know this. Listen. If A and B are invertible matrices of the same order, then we can say A into B, inverse of A into B is the same as finding B inverse separately and A inverse separately. This property looks somewhat similar to the transpose of a matrix, because when you're finding the inverse, right, you do one of the steps, you do transpose of the matrix, which you will understand in the next chapter. I need to discuss a term called as adjoint of a matrix. So AB inverse is also equal to B inverse into A inverse. Okay. So that is all with respect to the theory in this chapter. Okay. So what I'm expecting is, for the next 3 to 4 days, you guys work on the problems. And in Monday's class, we will discuss the doubts. Then we'll go to the next chapter. If you have doubts, we'll discuss it on the day. If no doubts, we can start the next chapter, that is determinants. Okay. But before that, I'm sharing just a minute. Yes. So if you check the WhatsApp group of 2022-23 12th batch, I have shared an exam schedule, okay, where you will be having some tests in inverse trigonometric function, continuity and differentiability, and applications of derivatives, where enough breathing space is given between each chapter. Okay, so you start preparing accordingly. In the meanwhile, you keep working on this chapter also, since this chapter and the next chapter are not tough. So I'm assuming that you can solve things faster. Okay, so make sure you're managing your time properly, and any kind of help needed, reach out to me on the student support number. So that is a number from which I messaged you now. Okay, is that clear?
Yes.
Okay. Any other doubts that you have? Okay. So that's it from my side for today. We'll wind up. Okay. So you keep working on the problems and don't wait for me. Any doubt, reach out to me on the student support number. Okay. So let's wind up this.
Thank you, sir.
Thank you, sir.
Thank you, sir.
So tomorrow it's offline, right?
Tomorrow there is no class, no? Chemistry, yeah. Yeah, chemistry will be offline. Yeah.
Okay, sir.
Because I'm not well, I conducted online.
Yeah, okay, sir.
Okay. Yeah.
Thank you, sir.
Okay.